All right, today we're going to go through chapter 18. We're going to go through most of it today. We'll finish up on Monday, and then we'll start working some problems. For the test is next week on Thursday. All right, chapter 18 is thermodynamics and equilibrium. All right, so we're going to start with the first law of thermodynamics. All right, so thermodynamics, we're just going to study the heat and other forms of energy involved in chemical or physical processes. So thermodynamics is about the heat and energy of chemical reactions. All right, and so the first law of thermodynamics is your delta U is equal to Q plus W. All right, and so your Q is your heat and W is your work. And so this is your heat and this is your work. And that is equal to the delta U. That is your internal energy. That is the sum of kinetic and potential energies of the particles making up the system. So we're going to talk about heat and work in the first law of thermodynamics. All right. So work, you're going to be moving a piston, so that is work, and that would require a change in volume of your gas. And so the work equation is negative P delta V. All right, so if you're changing your volume, the piston is going up and down, then you are doing work. All right, so if you do not have a change in volume, then you do not have any work. So if your piston is locked in place, then there is no work in that system. All right, so here we rearrange it. So your delta U is equal to Q plus W. All right, and if we are at constant pressure, all right, and so here we're talking about a constant temperature and a constant pressure. All right, if we're at constant pressure, Q is equal to delta H. All right, and so our delta H then is equal to Q. I like to put a sub P here to indicate that your delta H is your Q at constant pressure, which is how we're going to run most, if not all, of our problems. There might be a couple that are constant volume. All right, and so we can then put in a delta H for the Q position. All right, and then the work, again, work is equal to negative P delta V. All right, and so they're just putting PV, but at constant pressure, the pressure is staying the same, and then we are changing a volume. And so when you rearrange that, you get the delta U is equal to delta H minus your P delta V. And so they have rearranged it here. They added the P delta V to both sides. And so they have then their delta H is equal to delta U plus the P delta V. All right. And so they just did a substitution in for work and for the heat. Note, if we are at constant volume, then your work is equal to 0. So work is equal to negative P delta V. And so if there is no change in volume, so that means delta V is 0, then of course anything times 0 is 0, and your work is 0. If we go back up to our first law of thermodynamics, which is the delta U is equal to the delta H plus the work, when we are at constant volume, you put in 0 for the work. And so you have your delta U is equal to, and instead of the, wanted to put the first law of thermodynamics, delta U is equal to Q plus W. All right, so Q, that should have not been delta H because it's only delta H at constant pressure. So again, your delta H and your Q, that is only at constant pressure. When you're at constant volume, you see that delta U is equal to Q. Then I put a V here to indicate that we are at constant volume. So QP, heat at constant pressure, is your delta H. Heat at constant volume is your delta U, because the first law of thermodynamics, and we know that if you have zero change in the volume, you're going to have zero amount of work. All right, and so your delta U is equal to Q at constant volume. Your delta H is equal to Q at constant pressure. All right, so what we did in chapter 6, we found the delta H of reactions. All right, and so we have the delta H is the products minus the reactants. We are going to find two other things the same way. We're going to find a delta S, and that's going to be the same thing here, except it's going to be the S of the products minus the same thing here, the S of reactants. All right, and then recall the little circle here on top means standard temperature and pressure. All right, and so the standard temperature and pressure, the little circle here indicates 25 degrees Celsius and 1 ATM. We're also, now these are interesting because this, we can use a table at any temperature. So use a table, whatever table number we have for these. Use a table for data. All right, so you get your products and your reactant numbers from this table at any temperature. All right, and so it is going to be given to you at 25 degrees Celsius and 1 atmosphere. We can use this table, whatever table has delta H values, whatever table has the S values, we can use that for any temperature. So your delta S and delta H are independent of temperature. All right, so that means use them at any temperature. And then later, we're going to get a delta G, and we're going to do it the same way. And we're going to get delta G of your products minus delta G, not reactants. And now this one is going to be noted a million times, so don't mess it up. This is only 25 degrees Celsius. Only at 25 degrees Celsius. If it is not 25 degrees Celsius, you cannot use the numbers off of the table. Delta H, delta S, doesn't matter what they say the temperature is, we can use the tables. Delta G is highly temperature dependent, and we cannot use delta G unless the numbers off the table, unless we are at 25 degrees Celsius. Now, the delta H and the delta S do change with temperature, but they change very, very small amounts. And so that small amount of change is insignificant for our calculations. And so we say that it is going to be a constant at any temperature. All right, so we're going to talk about a spontaneous reaction. All right, so that can be a physical or chemical change that is spontaneously going to go to products. When you have spontaneous, that means you have your reactants, and they spontaneously react, and they give you your products. All right, so an example of a physical process, if you take an ice cube out of the freezer. All right, so the freezer is very cold, below 0 degrees Celsius. The room temperature is higher than the freezing point at 0 degrees Celsius. So H2O solid is going to convert to H2O liquid. So you set it on the table and you will then have your liquid water. All right, so that is going to spontaneously happen at room temperature. All right, so we also know that we have to heat the ice in order to make it a liquid. So we have to remember that when heat is a reactant, then we know that the delta H is positive. Anytime your heat is a reactant, you absorb the heat, Delta H is positive, and we call that endothermic. If we reverse the reaction, and we have our H2O liquid going to H2O solid, we know that we also know the same thing. Anytime you reverse the reaction, you change the sign of your delta H. All right, and so of course now heat is on this side. We reverse the reaction, and so now delta H is negative, and it is exothermic. So anytime you reverse a reaction, you change the sign of your delta H. All right, now if we go back to our first one where we took the ice cube out of the freezer and we said that that is going to be spontaneous. This is spontaneous. We don't have to do anything else to it. It is spontaneous at 25 degrees Celsius that your ice cube is going to melt into water. All right, so I also said that your delta G is temperature dependent. What I didn't tell you is delta G is going to determine whether a reaction or a physical process is spontaneous or not. So if your delta G is negative, then it's spontaneous. If, of course, it's positive, delta G is positive, then it is non-spontaneous. All right, and so we don't need to calculate delta G. We look at this and we know that if we put an ice cube on a table at 25 degrees Celsius, it is going to melt into water. And so we know that at 25 degrees Celsius, the delta G is negative. It is spontaneous. The ice is going to melt. All right. If we did the same thing down here and said we took water and we put it on the table and at 25 degrees Celsius, it is not going to spontaneously turn into an ice cube. All right. And so this one is not spontaneous. Liquid water does not freeze unless you stick it in the freezer. All right. And so here your delta G is positive. This is non-spontaneous at 25 degrees Celsius. All right, so I said delta G is highly dependent on temperature. If I gave you this process and I said we are at minus 25 degrees Celsius, so you stuck it in the freezer, now you've got water in the freezer, and next time you look, it's ice. It is spontaneously going to turn into ice. So at minus 25 degrees Celsius, now your delta G is negative. It is spontaneous. If you put water in an environment that's negative 25 degrees Celsius, it is going to freeze. That is it. So it's going to spontaneously, the liquid is going to turn into ice. Nothing else has to be done. You stick it in something that's below its freezing point, it is going to freeze. Above its freezing point, it is going to melt. All right, and so the delta H is going to be the same. The delta S is going to be the same. The delta G changes. And that tells you if it is spontaneous or not. All right, so here's just a rock going down the hill. If you push a rock down the hill, it's going to go. And there's not going to stop until it levels off enough. All right, but the rock is not going to spontaneously be at the bottom of the hill and go up the hill. All right. All right. So I talked about delta S, and delta S is the second law of thermodynamics. All right, and so it is entropy. If you look up the word entropy, it means disorder. All right, so it is going to more disorder. All right, and so your entropy, that is your S. All right, again, you're going to have a table with S values. If you want the delta S of a reaction, products minus reactants will give you that value. Now, disorder is what it is measuring. And so solids are very ordered. Liquids have quite a bit of order. Gases are all over the place. Gases have a large entropy amount. It is lots of disorder in a gas. So when we look at a reaction, we're going to look at the gases on the left and right. So if you have on your reaction going on. You've got, let's say, 2 gases on this side, and you have 3 gases on the other side. All right, so 2 gases, 3 gases. All right, so we're looking at the moles of the gas. All right, so you have 2 moles of gas on the left, 3 moles of gas on the right, balanced chemical reaction. All right, and so you see that 3 gases is going to be more disorder. And so 3 gases, more disorder than 2 gases. All right, and so you have a delta S that is going to be positive. All right, if you had 2 gases on this side, and now it's only going to 1 gas, now you have 2 moles of gas in balanced chemical reaction, 1 mole of gas on the right side. Now you're going to more order. All right, and so you will have less disorder. Delta S is disorder. You will have less of it. Delta S would be negative. All right, and so when you have the same number of gases on both sides, and solids and liquids, then your delta S is going to be approximately 0. So if you had 2 gases and it goes to 2 gases, all right, so your delta S is going to be essentially 0. It's not going to be absolute 0. It's going to be a very small number. It's not getting more order. It's not getting more disorder. It's essentially staying the same. All right. No. Okay. So here, if you have your gas contained in whatever volume this is, say it's 1 liter. All right, and now you open up this stopcock, and now you have your gas going throughout 2 liters. Now you have more disorder. Here they're more ordered all together, and in the second one, they are more spread out, more disorder. And so this process would be a positive entropy process. More disorder is happening. All right, so as I said before, you're going to have your delta S of any reaction, and so it's final minus initial. All right, and anytime you have a final minus initial, you're going to have a delta here, and those are called state functions. So when you have final minus initial, so pretty much delta anything. So delta S, delta H, delta G. All right, so these are called state functions. All right, and so that just means it doesn't matter how you get there. It's where you started and where you ended. All right, what is not a state function, and you'll never see a delta W because work is not a state function. So if you were coming to class and you started at main campus, you're coming to North Campus, well, that would be the least amount of work that you could do to go from main campus to North Campus. But if you're hungry and you stop at McDonald's and then you're going to do a lot more work. But you're saying I started at main campus and I went to North Campus. Again, it depends on the path, how much work you're going to do in order to get from one place to another. And so it's not just the final minus initial for work. It is how did you get there? It is path dependent. So if you are a state function, it doesn't matter which path you took. It is simply where you started and where you ended. The units, all right, so delta H on our tables, you'll see all of our tables, delta H units will be in kilojoules per mole. All right, every, usually next is S. And note that it's not delta S, it is simply S. Not that I would care, but it's interesting that this is just S, not delta S. So now your S is going to be in joules per mole Kelvin. And your delta G is going to be given in kilojoules per mole. So your delta H and your delta G both in kilojoules per mole, but your entropy, your S value, is going to be joules per mole Kelvin. All right, so let's say we take a milligram of solid iodine at room temperature. Later you notice that the iodine has sublimed. All right, so we have I2 solid going to I2 gas. All right, so iodine skips the liquid state. It goes right to the vapor state. All right, so what can you tell about the entropy? Again, you would look at the number of gases. You have 0 gases on the left, going to 1 gas on the right. You're going to more disorder. Solids are very ordered. You're going to a gas, lots of disorder. And so the delta S for this reaction is definitely going to be positive. All right, and then you go to one of the tables, you can look up the S value for the gas, S value of the solid, and get the actual delta S for this reaction. For this reaction, you can also predict delta H. You can't always predict delta H, but for many of these things you can. You know that you're going to have to heat a solid in order to turn it into a gas. And so we also know that our delta H is going to be positive, and it is endothermic. So we're going to more disorder, and the reaction is endothermic. All right, so delta S is the second law of thermodynamics. And so since it is the units of delta S is your joules per Kelvin, all right, that is going to be then Q. We're going to get our heat in joules Q over the temperature T in Kelvin. If you ever see a T, the T must be in Kelvin. All right, so you can have delta T, that can be in Celsius, it can be in Kelvin. A change in temperature, a 1 degree change in Celsius is the same as a 1 degree change in Kelvin. But if you just have T, it must be in Kelvin, because 0 degrees Celsius we get all the time. That's the freezing point of water. You try to put in a 0 in a denominator, you're going to get an undefined answer for your answer. All right. Anytime you have T by itself, you must put that in Kelvin. All right, so here we have another process, and this one is 1 mole of gas on the left and 2 moles of gas on the right. All right, so they are both gases. But of course, when you go from 1 mole of gas to 2 moles of gas, you have more disorder. And so here you know that the delta S is going to be positive. Here is one where you cannot predict the delta H. We're not familiar with this reaction. We cannot predict whether it is going to be a negative or a positive. You got to get your chart, get your answers by taking the products minus reactants for delta H to determine if it is endothermic or exothermic. All right, but we are able to predict delta S for any reaction. Any reaction, we can predict the sign of delta S. We can't always predict the sign of delta H. All right. I think I skipped. All right. So, yeah. All right. So you have, whenever you're doing a phase change. So when we had the solid going to a gas, when we had our liquid going to a solid going to a liquid. Anytime you are not changing the identity, H2O gas, H2O liquid, H2O solid, H2O liquid. All right, so that is a phase change, not a chemical reaction. All right, anytime you have a phase change, then you have your delta S, and we'll call it of vaporization first. That is equal to your delta H of vaporization divided by the temperature at the vaporization temperature. All right, and if you had delta S of fusion, that's equal to your delta H of fusion over your temperature of fusion. All right, and so you have your phase changes. Now note what we're going to find is that a phase change is when it's at its temperature, it's at a perfect equilibrium. All right, when you have at a perfect equilibrium, delta G is equal to 0 at equilibrium. All right, so if we are freezing water and we're at 0 degrees Celsius, it is not spontaneous to the right, it is not spontaneous to the left, it is in a perfect equilibrium. And so the delta G is 0 at equilibrium. Of course, if we raise the temperature to above 0, then it is going to melt. If we lower the temperature below 0, it is going to freeze. All right, so the heat of vaporization of carbon tetrachloride at 25 degrees Celsius is 39.4 kilojoules per mole. All right, and so we can then calculate, once we have one or the other, we can calculate the other one. We know that the delta S of vaporization is equal to delta H of vaporization divided by the temperature of vaporization. And so when they give us the delta H, that is 39.4, and I'm going to go times 10 to the third joules per mole, but we have 1 mole in our balanced chemical reaction. And then the temperature, again, has to be in Kelvin, 298 Kelvin. I converted it to joules because I'm calculating delta S, and delta S is in joules per Kelvin. And so your delta S of vaporization, when you take your 39.4 times 10 to the third and divide by 298, you get 132. All right, so this reaction has a delta H of vaporization of 39.4, and we could have predicted that. We know that when we have a liquid changing to a gas, this is not a chemical reaction, this is a physical process. CCl4L, CCl4G, we're just changing a phase. This is a phase change. All right, we have to heat our liquid in order to boil it. So we knew this would be endothermic. We predicted that. We know we have to heat a liquid to make it a gas. And so we know that delta H is positive and it is endothermic. In order to get the number, we would have to have the chart, products minus reactants. They did that for us, and it is 39.4. All right, so now we have our delta S, and it says that the liquid carbon tetrachloride at 25 has an S value of 216. All right, so we look on our chart. The liquid is given, the gas is not. So the S value here, that is the question. It is not listed on the chart. But we know for any reaction, the delta S is equal to your products minus reactants. But we have our answer for delta S. It is 132. The product, we don't have that one. We do not know the S value for CCl4 gas. It is not listed on our chart. The CCl4 liquid is listed on the chart. It is 216. And so to solve this, we just have to add 216 to both sides. And we get a 348. All right, so that is the S naught value for CCl4 gas. All right, and so what we did know before we got our answer of 348 joules per Kelvin is that the liquid was 216. The S value is 216. When we compare the liquid to the gas, we know the gas has much more disorder, which means that number has to be greater than 216. And so that number is 348 joules per Kelvin. All right. All right, so now we're going to calculate whether a reaction is spontaneous or not. So the equation, a very, very, very important equation, is your delta G is equal to your delta H minus T delta S. All right, and so when your delta H minus T delta S is less than 0, that means delta G is negative. If delta G is negative, then you are spontaneous. And when you calculate your delta G is equal to delta H minus T delta S, if you get a delta G that is positive, then it is non-spontaneous. All right, so again, we did water freezing. Your delta G is highly dependent on the temperature. Your delta H and your delta S are independent of temperature. So delta H and delta S are independent of temperature. All right. All right, so it doesn't make any difference what the temperature is. You go to the chart, products minus reactants, that is your delta H at any temperature. Delta S, products minus reactants, that's your delta S at any temperature. Delta G, products minus reactants, that is only at 25 degrees Celsius. If you are at any other temperature, you must find delta G by getting the delta H, which is independent of temperature, and the delta S, that is independent of temperature, and putting in your temperature value. Of course, that is a T, must be in Kelvin. Make sure you always have your T's, temperatures, in Kelvin. All right, and so that is the third law of thermodynamics. All right, so, well, it is a substance that is perfectly crystalline at 0 Kelvin, has an entropy of 0. All right, so we're talking more about entropy. Note that the circle, the standard conditions, the little knot here on top of your delta H's, your delta S's, the S's, all right, these are standard states. So we're talking about 1 atmosphere and 25 degrees Celsius. I don't know if it says anything, whatever. All right, so 25 degrees Celsius, 1 atmosphere. Now, if you are a gas, your gas pressure is 1 atmosphere. So any gas that we're talking about with the little circle here, that is going to be 1 atmosphere of pressure. Any aqueous solution is 1 molar of that solution. So your standard state has a 1 atmosphere, 25 degrees Celsius. So all pressures are 1 atmosphere, and all molarities are 1 molar for the standard state. All right, so here's values for your entropies, and we already did an example, but if you look at bromine liquid, your number is 152.2, and if you look at the gas, it is much higher at 245.3. Of course, gases have more disorder, more entropy than a liquid. All right, and then also always note the units. These are joules per mole Kelvin. All right, so again, we can predict whether we're going to have a positive or a negative entropy value for any reaction. So here's a reaction where we have no gases and 1 solid going to 2 liquids and 2 gases. All right, so this is a lot of entropy that's being formed. We had a lot of order, 1 solid. Now we have 2 liquids and 2 gases. So this is going to be a large delta S value, a delta S being positive. You can calculate the number. You take the table that we just saw, you take your S values, add up all your products, add up all your reactants, products minus reactants, and you will get your delta S value. All right, so calculate delta S. So first we can look at it and see what sign that we are going to get. And you see that in this example, we have two NH3 gases. So we have two gases here plus one gas here. So we have a total on this side, 3 gases. And then on this side, we have 0 gases. We have an aqueous, we have a liquid, we have no gas, we have 3 gases, disorder all over the place, going to more order or less disorder. And so when you have less disorder, that means your disorder is less, negative. Delta S is negative. All right, so now we can actually calculate the number. The values are given to us. NH3 S value is 193. CO2 S value is 214. The NH2CO NH2 value is 174. The H2O liquid value is 70. And these are all in joules per mole Kelvin. All right, so all of these are in joules per mole Kelvin. And so for the NH3, we have 2 moles. So you have to multiply it by 2. So you multiply this by 2, you have then your 6, your 8, and your 3, 86 joules per Kelvin. And so when you had 1 mole of this times 214, you get 214 joules per Kelvin. And when you had 174 times 1 mole of that, you get 174 joules per Kelvin. And when you have 70 joules per mole Kelvin times 1 mole, you have 70 joules per Kelvin. All right, and so to get the delta S of this, you take your products, add them together. And so you got a 244. So you have your 244 minus your reactants. You add up your 386 and your 214, and you get 600 joules per Kelvin. And so we do get a negative value. So our delta S for this reaction is negative 356 joules per Kelvin. So we knew that we would get a negative value because we had 3 gases going to no gases. And just using the table, we can get our values and calculate the actual number. And it is negative 356 joules per Kelvin. All right, so I already wrote this equation, and that is your delta G is equal to delta H minus T delta S. This is a very important equation. All right, so a lot of things we can predict the signs of our delta H and our delta S, and once we know those, we can then predict what delta G, how delta G is going to react to those conditions. All right, so this is Gibbs free energy, that's G. All right, and so we have our delta G is equal to delta H minus T delta S. Again, remember your delta H, your delta S, always off the chart. Delta G, you can only use the delta G values off the chart when it's 25 degrees Celsius. This equation can be used at any temperature. All right, so if you have a delta G question not at 25 degrees Celsius, you must use this equation, but this is good at all temperatures. All right, so products minus reactants, only 25. So if the question is to calculate delta G, and you do delta G products minus delta G reactants, this again is only at 25 degrees Celsius. All right, if you're asked for delta G at any other temperature, you must use the delta G is equal to delta H minus T delta S. All right, so again, when you do your delta H is delta H products minus delta H reactants, and your delta S is your S products minus S reactants. This is at any temperature. All right, so it's not exactly the same when you change temperature, but again, the amount of error that you get is not significant for this class, so we are going to say that your delta H and your delta S are independent of temperature. Get it at 25. That's what it is at any temperature that the question is asking. Delta G is highly temperature dependent. All right, so again, the little circle, or just going through it again, your little circle means you are at 1 atmosphere and 25 degrees Celsius. Any concentrations are 1 molar. Any partial pressure of gases, 1 atmosphere. All right, so this one, we want to find the delta H of this reaction at 25 degrees Celsius. All right, so you can always find your delta H and your delta S. So you can find your delta G by taking your delta H minus your T delta S. And you would have to do this way if they didn't give you a delta G chart. They only gave you a delta H and a delta S chart. That works at any temperature that they give you. If they do give you a delta G chart, you have the temperature is 25. So this is the case where you could use that one, or you can do delta H, delta G is equal to delta G products minus delta G reactants. So when you're at 25 degrees Celsius, you can use either one. If you are not at 25 degrees Celsius, you can only use the delta H, delta G is equal to delta H minus T delta S. All right, and so you find your values, so they're going to do it this way. So it doesn't matter. They're going to go, I'm going to do this problem this way. So you find your delta H. All right. When I looked at this reaction, I could not predict whether this reaction would be exothermic or endothermic. This is not one that you can look at and predict. You put the numbers down and you get it. What you can predict is the sign of delta S. So you see that you have 1 mole of gas plus 3 moles of gas. You got 4 moles of gas. On the reactant side, you are producing 2 moles of gas. On the product side, you're going to more order. You're going to less disorder. Delta S, less disorder, will be negative. All right, so when you calculate it, remember your delta H, elements in their natural state are going to be 0. All right, you got your negative 45.9 kilojoules per mole. You got your 2 moles. So you got your negative 91.8. So that's it. So the delta H for this is products negative 91.8 minus reactants 0. So that is the delta H for this reaction. It is exothermic. And so that is your delta H. Your delta S will be negative. All right, so you take your 2 times your 192.7 and then subtract the sum of 191.6 and 3 times 130.6. And 3 times 130.6 plus 191 is greater than 2 times 192.7. That gives you a negative value. When you push the buttons, you get a delta S of negative 198 joules per Kelvin. But the question wasn't what's delta S or what's delta H. The question is what is delta G? So to find delta G, that is equal to your delta H minus your T delta S. All right, but you have to be careful because your delta G is usually given in kilojoules and delta H is given in kilojoules, but your delta S is given in joules per Kelvin. You cannot be subtracting joules from kilojoules. You have to subtract kilojoules from kilojoules or joules from joules. You have to have the same units. When I do this equation solving for delta G, I always put it in kilojoules because delta G is normally given in kilojoules. And so I will write it, my delta G, my delta H, that is in the correct units, negative 91.8 kilojoules, minus my temperature is 25 degrees Celsius. So that is 298 Kelvin. And I have to convert my joules into kilojoules. And so that is a negative 0.1980 kilojoules per Kelvin. And so your kelvins cancel, and now you have kilojoules minus kilojoules, and so you have to have the same units. You can pick joules if you want. For delta G, I will pick kilojoules. So when you plug that in, you get a delta G of negative 32.8 kilojoules. All right, and so because we have a negative value for delta H, we know that that is exothermic. We have a negative. We already predicted the delta S value is negative because we had our more moles on the reactant side than we had on our product side. So we knew that we were getting less disorder. Now we have calculated the delta G, and the delta G is negative. That means this is spontaneous. So anytime your delta G is negative, it is going to be spontaneous. All right, so free energies of formation. All right, so just like we did delta H, we're going to have our chart again of delta G's, and it is the free energy of formation. All right, and so to form an element in its natural state, that is a 0 value, just like it was for delta H. So all delta H's that are 0, those delta G's will also be 0. It is the energy to form them. All right, and so when we look and we have calcium solid right off the periodic table, it's 0. Carbon in its natural state is graphite, not diamond, not buckyball, and that's when you have the 0 in its natural state. Chlorine gas, 0. Fluorine gas, 0. So again, elements in their natural state are going to have a delta G value of 0. But here's the chart. Now the key here is that you might want to put on top of this chart is only at 25 degrees Celsius. All right, you have to be sure that you're only using delta G at 25 degrees Celsius. Delta H and the S values, doesn't matter what the temperature is, but delta G only at 25 degrees Celsius. If you are not at 25 degrees Celsius, these are not your numbers. All right, so again, when you're doing this, only at 25 degrees Celsius. There might be a reason why I keep saying that. Yes, people use this for any temperature. That's wrong. Only at 25 degrees Celsius. All right, so calculate delta G for the combustion of 1 mole of ethanol at 25 degrees Celsius. All right, so we have 25 degrees Celsius. We can use our numbers off of the table because we are at 25 degrees Celsius. All right, well, we can predict. Let's first predict our delta S. Our delta S prediction is we have 1 liquid and 3 moles of gas. And on the right, we have 5 moles of gas. 2 CO2 gas, 3 H2O gas. So we have 3 moles of gas going to 5 moles of gas. So we know our delta S for this reaction is positive. We're going to more disorder. We also recognize this. We don't even have to recognize it because they tell us in the question that you're doing a combustion. And by understanding what combustion means, you know that combustion is a release of heat. All right, you get heat and light. And so we know that any combustion reaction is going to produce heat. And anytime you produce heat, your delta H is negative. You are exothermic. So we know our delta H is negative. We know our delta S is positive. Now we just have to calculate our delta G. But can we predict the sign of delta G? Well, sometimes we can, sometimes we cannot. All right, so we do know that delta G is equal to delta H minus T delta S. And we also know that temperature is in Kelvin and it has to be positive. There is no negative T. There is no negative temperature in Kelvin. Absolute zero, everything is nothing exists. So zero is as low as it can go, and then that's when nothing exists. So your temperature is always a positive value in Kelvin. All right. So we've calculated our delta H is negative, and our delta S is positive. So if you do the math, temperature always is positive. So this is negative, and then we have to subtract another number, so it's going to be even more negative. And so we know that delta G is negative at any temperature. All right, and this is only true when your delta H is negative and your delta S is positive. And so we know the sign of this one. We know that delta G is negative, and this is spontaneous. All right, so now we get to our chart, look up our numbers, and get our answer. All right, so there are the numbers. Again, it's in kilojoules per mole. So 228.6 kilojoules per mole. And we have to multiply it by the 3 moles. Negative 394.4 kilojoules per mole. Multiply it by the 2 moles. Oxygen is an element in its natural state, 0. Negative 174.9 kilojoules per mole, 1 mole of that. So you add up your products, and then you subtract your negative 174.9, and that will leave you with a negative number, negative 1,299.7. All right, and so this is spontaneous. So we predicted the negative, we got the negative, and it is spontaneous. All right, so I said that your delta G is highly temperature dependent. In this reaction, it doesn't matter what the temperature is, your delta G will always be negative and spontaneous. That is not true for all reactions, but it is true for every reaction that has a negative delta H value and a positive delta S value. All right, so I said negative delta G is spontaneous, so I have to update that a bit. If you are within 10 of your 0, so in order to be spontaneous, you have to be less than negative 10, all right? To be non-spontaneous, you have to be greater than positive 10. If you are between the negative 10 and the positive 10, then you are in equilibrium. All right, so if you have a delta G and you calculate it and it is negative 8 kilojoules per mole, all right, this is at equilibrium. All right, so you wouldn't call that spontaneous. You would say that's at equilibrium. So what does spontaneous mean? That means you got all products. All right, so spontaneous, the reaction went to the right, you got all products. No more reactants, all products. If it's non-spontaneous, that means that the reactants have stayed there and you didn't get any products. It is not going to go anywhere. It's staying on the left. If you're at equilibrium, that means that you're going to have a significant amount of both products and reactants. And so when your delta G is between plus and minus 10 kilojoules per mole, you are said to be at equilibrium, which means you have a significant amount of both products and reactants. All right, so again, if delta G is equal to a positive 6 kilojoules per mole, again, that is considered to be at equilibrium. All right, but of course, if delta G is negative 20 kilojoules per mole, then you are spontaneous. So the number is, if it's between the 10s, then it's at equilibrium. If it is less than minus 10, it's spontaneous. If it's greater than positive 10, it's non-spontaneous. All right, so here's a reaction that we are forming NO. So here, if we're predicting our delta S, we would say we have 1 mole of gas here, we have 1 mole of gas here, so we have 2 moles of gas on the left, and we have 2 moles of gas on the right. So we have 2 moles of gas going to 2 moles of gas. And so your delta S is very small. It's going to be essentially 0. It's not going to be absolute 0. It's just going to be very small. All right. So for the reaction as written, your delta G is 173.20 kilojoules. All right. So that is greater than plus 10. This is plus 173.20. And so this is non-spontaneous. All right, so that means the reaction is not going to the right, which means you have a ton of reactants and very few products. All right, and so that's what it's saying here. This is non-spontaneous. We know that because we have a positive delta G that's more than 10 kilojoules. And so the NO concentration, it is not going to the right. It is not forming any NO. And so your NO concentration is an extremely small number when you are at equilibrium. If your question is asking you to calculate the work max or the maximum useful work, all you need to do is calculate your delta G, because your Gibbs free energy is equal to your work max. So if you are finding the delta G, you are also finding your work max. All right, so here's where the equilibrium comes in. Your delta G is related to the equilibrium constant. So I said if you have a spontaneous reaction, it's going to the right, you're going to have a lot of products, which means you're going to have a large K value. If you are non-spontaneous and all the reactants are staying there and you have very few products, you're going to have a very small K value. All right. Note that we're going to be talking about a different kind of K. So far we had what? KC, we had KP, we had KA, we had KB, we had KW, we had K, I don't want to keep writing delta, KSP, and KF, and KD. Now we're going to have a KEQ. When you do the KEQ, the equilibrium constant K, KEQ, if you are a gas, you have to be put in partial pressure. So all gases in pressure, in atmospheres. All aqueous is going to be in molarity. All right, so it is going to combine, basically it combines your Kc and your Kp. If you're Kc, everything's in concentration. If you're Kp, you're only gases in pressure. If you're KEQ, if you're a gas, it's in pressure. If you are an aqueous, you are in molarity. All right, so if we write our equilibrium expressions for the KEQ here, all right, we have an aqueous, so that is a concentration of NH2CONH2. Liquids and solids are never put into any equilibrium constant. We don't put in liquid water. Over, these are gases, so now it is the pressure of NH3 squared, and CO2 also pressure of CO2. And so your units, although K values do not require units, but if I said give the units of this KEQ, you would have molarity in the numerator, you would have atmosphere squared times atmospheres, you would have atmospheres to the third, all right? Because all of your concentrations are in molarity, all of your gases are in atmospheres, all right? And so that is a KEQ. No, if you wanted to do KC, then these would both be in concentration. If you wanted to do KP, you would not include the aqueous solution. So this is a unique K value, this KEQ. Now the second one is not unique at all. We know that one. And so our KEQ is the concentration of Ag plus, concentration of Cl minus. All right, so this is the first K value where it's not the same as Kc. All right, so this KEQ is the same thing that you would get if you wrote the Kc. And it is also we know now, after doing the previous chapter, this is a KSP. Anytime you have a solid going to its ions, you have a KSP. All right, so sometimes your KEQ can be the same as something else, and sometimes your KEQ is unique to KEQ, and that is where this one is. All right, so you have your Q value, that is your reaction quotient. So this is a non-equilibrium. Put in your concentration of products over your reactants. All right, so at equilibrium, your delta G is equal to 0 and your Q is equal to K. So at equilibrium, so it was stated before, but when you are at equilibrium, if it says you're at equilibrium, your delta G is 0. All right, if you are at equilibrium, now you're not at a non-equilibrium concentration over product Q. You are the equilibrium constant, and I like to put KEQ there. All right, and so your equation becomes your delta G naught is equal to negative RT ln KEQ. All right, so this one, again, you always have to be aware of your units. All right, so in this one, your R value is 8.314 joules per mole Kelvin. All right, of course, T is always in Kelvin. All right, and then, of course, your KEQ, that is simply your equilibrium constant. All right, and now your delta G naught, that's your Gibbs free energy. All right, but the units for this Gibbs free energy, since you have 8.314 joules per mole Kelvin, this has to be in joules per mole. All right, so in order for your delta G and your R to have the same units, you either convert your delta G to joules, which is what I do, or you convert your R value to kilojoules. Either way. In this case, I convert my delta G into joules when I solve those. It would be exactly the same thing as if you converted your R to kilojoules. All right, so here, find the value of the equilibrium constant K at 25 degrees Celsius for this reaction. All right, and so for this reaction, we did the products minus reactants because we're at 25 degrees Celsius. And when we did that, our delta G for this reaction is negative 13.6 kilojoules. What does that mean? That means that the reaction is spontaneous. That means that we're going to have lots of products and very few reactants. However, this is on the borderline of equilibrium. All right, so if it was minus 10, then you would say it's at equilibrium. It is slightly lower than minus 10. It is minus 13.6, and so it's spontaneous. All right, so you're going to have more products than reactants, so the K value should be a large value. And when I say large value, a number that is greater than 1. All right, and so we can calculate it. The delta G is equal to the negative RT ln KEQ. Again, I convert my delta G into joules. So I put in negative 13.6, and I know K is times 10 to the third joules is equal to negative 8.314 joules. This is joules per mole, and this is joules per mole Kelvin. And my temperature, they give me right here, 25 degrees Celsius, and convert it to Kelvin for you, must be in Kelvin, 298 Kelvin, ln KEQ. All right, so you take your negative 13.6 times 10 to the third, all right, divided by your negative 8.314. All right, then you divide by 298 on both sides, and you get 5.489 is equal to the ln of KEQ. All right, and so then to get rid of your ln, you push your e to the x button. So e to that answer, and that gives you 242. So KEQ is equal to 242, or if you put it in scientific notation, 2.42 times 10 to the second. All right, so this is a large KEQ, has a positive exponent, so it is 242. That is greater than 1, so that is then a large KEQ value. That means you have more products than reactants. And we also have the setup. We already did that setup. Remember, the KEQ here was your concentration of NH2CO NH2 over your pressure of NH3 squared and your pressure of CO2. All right, so that one had the mixture of both molarity and atmospheres in it. So you can predict that you're going to have a spontaneous. So anytime it is spontaneous, that is going to be a large K value. And when I say large K value, that means that your K is greater than 1. When K is equal to 1, you're at equilibrium. So when you're at equilibrium, K is equal to 1, that means you have a same number of products as reactants. So greater than 1 is large, less than 1 is small. Let's go back to that answer. All right, so we predicted, get all of our numbers on this? Yeah, we predicted. All right, so here we're going to have our reaction here, your change in your free energy. So again, this is highly temperature dependent. All right, so again, delta G or K at another temperature can be ascertained by a simple method. In this method, assume that delta H and delta S are essentially constant with respect to temperature. All right, so we are always going to assume that our delta H and delta S are going to be the same regardless of the temperature. They are independent of temperature. The value of your delta G at any temperature can be determined by this equation. Again, if you are not at 25, you must use this equation to calculate your delta G. All right, so this table you might have to look at for a while to figure it out. This is a very important table. Your delta G is equal to your delta H minus your T delta S. We already did the first one. The first one says if I have an exothermic reaction, that's negative, and I'm going to more disorder, more moles of gas, and this is positive. All right, temperature always is positive. You can't have a negative Kelvin temperature. So if your delta H is negative and then you're subtracting a positive number, that's then more negative. So delta G is negative. And it doesn't matter what the temperature is. This temperature value isn't going to change it. If it's a higher temperature, it's more exothermic. If it's low temperature, it's less exothermic. But no matter what, it's exothermic. Exothermic. Yes, it's always exothermic because that never changes. It's a negative delta G. It's spontaneous. No matter what you do with the temperature, it is going to have a negative delta G. So if you go down close to an absolute 0, then your delta G is going to equal your delta H. And when your delta H is negative, well, that means your delta G is negative. And so no matter what your temperature is, you're going to be spontaneous if you have a negative delta H, exothermic, and a positive delta S going to more disorder. All right, if we do the opposite, if I have my reaction that is endothermic and a reaction that is going to give us less disorder, so we're going to fewer moles of gas, all right? So a positive delta H minus, of course, the temperature must always be positive, so your delta H is positive minus a negative value. When you subtract a negative value, it is a positive value. So no matter what you do with the temperature, you're always going to get a positive delta G. So this reaction would be non-spontaneous at any temperature. All right, so when they are both negative, so this is where this is an easy thing to remember. Delta H minus T delta S. When they are both negative, this is negative and this is negative. And we want the delta G to be negative, to be spontaneous. All right, so we want the delta H factor to dominate. In order for the delta H factor to dominate, we need to have a low temperature. So it's very nice that if your delta H is negative and your delta S is negative, you're going to be spontaneous at a low temperature. So negative, negative, low temperature. So when you have a negative and negative, you're going to be spontaneous at low temperature. So when it's negative and it's negative, low temperature, you're spontaneous. And so when you have the positive and the positive, when your delta H and delta S are both positive, then you're going to be spontaneous at a high temperature. All right, and so this is going to be when your delta G is equal to delta H minus T delta S. When this is positive and this is positive, then it's going to be spontaneous at high temperature. So negative, negative, spontaneous low temperature. Positive, positive, spontaneous at high temperature. And we will actually calculate that temperature because at equilibrium, delta G is equal to 0. And so when we plug in 0 is equal to delta H minus T delta S, and we solve for the temperature, so we add T delta S to both sides. That's equal to delta H. So your temperature is going to be your delta H divided by your delta S. So when I say it's going to be spontaneous at low temperature, you're going to find that temperature by taking your delta H divided by your delta S. So the temperature I'm talking about is the temperature that you get when you take your delta H divided by your delta S. Products minus reactants, divide those two numbers. Again here, remember, this is in kilojoules and this is in joules. You have to convert them to the same unit. You can convert delta S into kilojoules, or you convert your delta H into joules. But when I say a high temperature, that is all based on what number you get for your delta H over your delta S. So a higher temperature than that, a lower temperature than that. So it's when it says high temperature, low temperature, that is very generic. We are going to actually calculate that temperature. And we will do that on Monday.